Imagine standing on a flat plain before a wall of rotating wind 2.6 miles wide. This is the physical footprint of the largest tornado recorded. These storms can maintain their intensity for hours. This archival photo shows the aftermath of the 1925 tri-state tornado, carving an unbroken path of destruction through the American Midwest for 219 miles. Within that destructive footprint, wind speeds can surpass 300 miles per hour. These forces sweep concrete slabs clean, erasing entire neighborhoods from the earth. At the extreme high end of the scale, an EF5, these winds possess enough kinetic energy to deform the steel frames of high-rise buildings and loft heavy debris, like canceled bank checks, over 100 miles away. We have deployed networks of high-resolution Doppler radar, and we have thousands of trained spotters scanning the skies. Yet predicting the exact moment one of these funnels will actually connect with the Earth remains highly elusive. Meteorologists call this precise ignition point tornadogenesis. To understand how that microscopic connection happens, we have to pull back and look at the massive continental blueprint that builds the storm in the first place. This map visualizes global tornado frequency. Notice the scattered heat signatures over Europe, and then look at the massive anomaly sitting over the United States, which averages about 1,200 of these storms every single year. North America produces 4 times as many tornadoes as the entirety of Europe, because the continent itself acts as a topographical engine, uniquely designed to breed violent winds. Westerly winds hit the Rockies, forcing dry air down the eastern slopes. Simultaneously, the Gulf of Mexico drives warm moisture north. Without an east-west barrier, the dry air crashes into the humid Gulf air, creating highly volatile atmospheric instability over the Central Plains. Tornado Alley serves as the physical exhaust pipe for this continent-sized atmospheric engine. When that continental instability reaches a boiling point, it spawns a specialized class of rotating thunderstorm known as a supercell. As intense rain falls within the supercell, it drags a heavy curtain of cold air down with it. This is the rear flank downdraft. It grabs the storm's mid-level rotation and physically pulls it down toward the surface. Converging warm updrafts and cold downdrafts force the storm's rain-free base to sag, creating a dark, lowering structure called a wall cloud. As the rotation tightens and reaches the ground, the internal air pressure drops drastically. The center of the funnel becomes an incredibly powerful atmospheric vacuum. Looking at this cross-section schematic of a mature funnel, notice that the internal flow is actually directed downward. Unlike a hurricane that pulls energy up from a warm ocean, a tornado draws its water vapor and power directly from the parent cumulonimbus cloud above. At this mature stage, the storm has successfully compressed miles of atmospheric chaos into a single, highly efficient, ground-shredding pinpoint of energy. But the exact mechanism that birthed the storm eventually kills it. That cold rear flank downdraft wraps entirely around the funnel, choking off the warm surface inflow it needs to survive. Deprived of fuel, the vortex enters its dissipating stage. Because of the conservation of angular momentum, the massive funnel stretches and thins out into a contorted, twisting tube before roping out completely. When faced with these extreme forces, human intuition often fails us, particularly when we seek shelter in outdoor concrete structures. For decades, a myth suggested highway overpasses were safe havens. Look closely at this collapsed concrete pillar. Highway infrastructure is vulnerable to extreme wind loads. Taking shelter under an overpass is actually highly dangerous because of the Venturi effect. As wind is forced through the constricted, wedge-like space between the bridge and the ground, it drastically compresses and accelerates, turning the area into a high-speed wind tunnel. Similarly, the old advice to open your house windows to equalize pressure is completely false. A violent tornado will destroy a structure regardless, and opening a window only allows the wind inside, hastening the failure of the walls and roof. When confronted with the extreme physics of a supercell, our gut instincts are frequently and fatally wrong. Today, we track atmospheric moisture gradients across whole continents and measure wind shear from space. Yet these storms still occasionally strike without a warning siren ever sounding. Despite decades of chasing supercells with mobile radar trucks, meteorology still cannot pinpoint the exact microscopic trigger that finally connects a rotating cloud to the dirt. We have mapped the engine, but we still don't completely understand the spark. Ultimately, we remain at the mercy of the Earth's geography.